Okay, good afternoon, everyone. So this is lecture number 11. So we'll continue our discussion from last class. If you recall, in the previous lecture, we were discussing about impedance transformation networks, and we saw that there was a need to shift impedances either up or down. Especially in the case of a power amplifier, you will want to typically take your 50 ohm impedance and kind of convert it down to something like 12 ohms or 18 ohms, 20, 25 ohms, something like that. And you'll also want to convert the impedances higher also sometimes. Okay. Now something similar happens in many contexts, and impedance transformation is a very integral part of RF design in general and in RFIC as well, right? So in last class we looked at what was called as the L match, right? And L match was like you can do an upward transformation by putting, let's say, this is your you can say, okay, you have a load resistor RL, or let's, and if you do something like this, you would basically get an Rn which is greater than RL, or in other words, Rn is given by, let's say, RL times Q squared plus 1, right? Now downward transformation can be done basically by putting the element in in parallel with the impedance to be down converted, and here you will get a certain input impedance which can be taken as RL divided by Q squared plus 1. Now the inductor and the capacitor can be interchanged. Of course, the values will change. So you can have a low pass realization like this, or a high pass realization as well. Okay. So both upward and downward transformations can have both a low pass type network and a high pass type network. Okay. So depending on what you want the network to do at either the DC end or at very high frequencies, you can choose an appropriate thing. For example, if you want this network to act as an open circuit during for DC, then what you would do is basically you would take a low pass network like this, right? You don't want a short to ground, or in other words, or if you want a short to ground at DC and you want a very high impedance at, let's say, AC, you will do something like this. All right. So these are the things that we saw, and we saw that the relationship between the two impedances, the Rn and Rout, or the load and the input impedances, is Q squared plus 1. You have it scales by a factor of Q squared plus 1. And the disadvantage that we saw was that once F naught and transformation ratio, let's say RL by Rn ratio, is fixed, then what happens is Q is also fixed, right? You do not have any flexibility to have a separate, you cannot separately set the Q of this network. Okay, so if you want bandwidth, you kind of have to live with whatever transformation ratio you get. And on the other hand, if you want a particular transformation ratio, you will have to live with whatever Q and bandwidth you get. Okay, so that is the limitation of L match. And of course, the advantage of L match is that it's a very simple network, and it is very easy to design. And the way in which we looked at how you design these things, I'll also give you some practice problems which you can use. The job of the other element is basically to, for example, in this case, if this is going to up convert, the job of this inductor is just to make sure that the reactive part is cancelled out. Okay, and so on. Okay, so I introduced the concept of pi match networks. Okay, and I also mentioned that this can be understood as having, let's say this is the Rp, and let's say this is the Rn. All right. So this has a L, C1 and C2, and this can be understood as what? Two separate L match networks. So this L is decomposed into two inductors, L1 and L2. Okay. Now this L1 and L2 is an imaginary or mathematical way of kind of dissecting this inductor. Okay. In practice, you just have one inductor. This inductor is decomposed into two inductors purely on the mathematical and modeling level and not in practice. So don't get confused. Okay. So you have an RP, you have C2, C1, and let's say this is your Rn. Okay. Now, looking at this network, okay, and looking at, so this is basically a L match network, right? And this is another L match network. Now, what will this L2 C2 do? Will RP get converted to a lower impedance or a higher impedance? Come on, guys. Let's say if I'm going to stand here and look at the impedance here, let me call it as the intermediate impedance Ri. Will Ri be lesser than Rp or greater than Rp?
Less.
It will be lesser than Rp because Rp is in parallel. One easy way to know it is something is in parallel with something, so definitely the impedance will go down. Okay, so obviously Ri will be lesser than. By how much will it be lesser than Rp?
1 plus
q square plus
1 plus q square, or rather
q1
let me
square.
just call it as the q right squared plus 1, just to differentiate between, you know, the right hand side L network and the left hand side L network. Okay, so q right squared plus 1 is the ratio. In other words, q can be written as what? Root of Rp by Ri minus 1. Okay, let's say this is q right. All right. Now, how about the left-hand side L match network? What is the relationship between, let's say, Rn and Ri?
Rn is equal to Ri into q left. I mean, q left square.
It will be higher, right? So yeah. Rn is going to be higher than Ri by a factor of q left squared plus 1, right? So this means that q left can be written as root of Rn divided by Ri minus 1. Okay, so far so good. All right, so now let us look at this network and then see what can be, you know, you have L2, we'll just look at the right hand side network now. Okay, you have L as well as C. So basically you can write two different Q equations. So what are the two different Q equations that you can write for the right hand side network? If you consider this particular part, okay, if you look at this particular part, it is C2 and Rp in parallel. So for a parallel RC network, what is the Q? It is omega naught C2 into Rp, right? So that is the Q. If you see, this can also be thought of, okay, for the inductor, you can think of it as what? L2 in series with Ri. Okay, so as I mentioned in last class, although you may not have the capacitor, when we talk about the Q of an inductor or the Q of a capacitor, even with just two elements, you can define Q, assuming that there is a, you know, the opposite element. Either for an inductor you have a capacitor, or for a capacitor you have an inductor, which is tuning it out at the frequency of interest. Okay, so Q right can be expressed as omega naught Rp into C2, and this is also equal to what? Omega naught L2 divided by Rl. Okay, it is a series RL network and it has an expression of omega naught L by R, and the value of resistance which this L2 is seeing in series with it is basically Ri. Correct. So these are the two expressions. Same way, what can we write for the Q left? So again, the inductor is seeing omega naught L1 divided by Ri, right? Is seeing in series resistance of Ri. Or the capacitor is seeing a parallel resistance of R in. So you can write it as omega naught C1 R in.
Sir,
Okay. Now the overall Q, can be designed as like, if you take this entire network, okay. So one easy way to define the Q is basically to say this L has a series resistance of R I, right? So you can basically say that omega naught L divided by Ri, which is nothing but omega naught L1 plus L2 divided by Ri, okay, which is nothing but what? Q left plus Q right. Okay, is this clear? So for the overall network, it is easy to, okay, somebody had a question. Okay, in the equation of Q right is the equation containing Ri of Rp. Okay, so for the capacitor, okay, it is C2 in parallel with Rp. Okay, C2 in parallel with Rp, and therefore it becomes omega naught Rp C2. It is L2 in series with Ri, right? So it becomes omega naught L2 by Ri. Okay, same way here, the series impedance, series resistance seen by L1 is Ri. So that is why you have omega naught L1 by Ri, whereas the shunt resistance seen by C1 is basically Rin. Okay, so that is how we define. I hope it is clear. Okay. Ri is the intermediate resistance, which does not include the inductor. It's just the resistance, not the impedance. Okay, so it does have a certain capacitive part, right, which is getting tuned out at the frequency of interest. So C2 prime will become C2 into Q squared divided by Q squared plus 1, which is approximately C2. Okay, so L2 and C2 will resonate at the frequency of interest, right? And you have Ri in series. So you can think of it as a series RLC network. Okay, let me just explain it. L2, let me say C2 prime, which is nothing but C2 Q squared by Q squared plus 1 with Ri. Okay, so this is a series RLC network where you can write it as, the Q right is written as omega naught L2 divided by Ri. Okay. Okay, good. So yeah, initially it can be slightly confusing, but once you understand it, like you can just directly keep writing like this. Okay, all right. Now, how do you design? So we came up with some equations and so on. Now the question is, let's say I want Rp to be transformed to a certain Rin. Okay, and this is to be done at a certain frequency. Okay, so for example, take this example. Let's say I want my 50 ohm to be converted to, let's say, 12.5 ohm. Okay, now this has to happen at a frequency of 1 gigahertz. All right, and I want a Q factor, overall Q factor of, let's say, 5. All right, so because I am having a pi match network, I have 3 degrees of freedom, which means that I can specify the impedance transformation ratio, the center frequency, and the Q of the entire network. Okay, now I will just outline the procedure. Okay, I want you to attempt doing it. This will also be good from your exam point of view. So I want you to attempt solving it on your own and see whether you are able to do it. Okay, now the kingpin in this whole thing is this impedance Ri. Okay, so the overall impedance, right, the Q overall is given by what? Omega naught L divided by Ri. So if you can figure out what is this Ri, okay, then you can set L. Once you set L, right, then you can basically, once you know that, you can basically find out the other components C1 and C2. The whole job in the design is to figure out what is the value of C1 and what is the value of C2. Correct? Okay. So let's see. So how can we write Ri in terms of Rin, Rp, and Q square? Okay. So if you look at, so overall Q overall can be written as what? Q left plus Q right. Okay, which can be written as what? Root of Rp by Ri minus 1 plus root of Rin by Ri minus 1. Okay. So if you equate the whole thing, it becomes, root of Rp by Ri minus 1 plus root of Rin by Ri minus 1 is equal to omega naught L by Ri. So now you have some, things which are in the power of 2 and so on. Okay. So an approximate way of writing it, okay, is basically to say this is the overall Q. An approximate expression, if you say, it is easy to solve this if you can neglect that minus 1 factor, right? So if you neglect that minus 1 factor, then what you would basically get is what? Root of Rp by Ri plus root of Rn by Ri is equal to omega naught Q squared basically. It's basically Q. So let's say root Rp plus root Rn is equal to, let's say, root Ri times Q. Right? You square on both sides, you get root Rp plus root Rn the whole squared divided by Ri is equal to Q. Now this is definitely a very approximate expression, and for lower values of Q it is not very good, but for slightly higher values of Q it is definitely worth doing it. But this is anyway a good starting point. Otherwise you will be going around in circles. Okay, you will have a lot of iterations. So a good starting point is basically to do that approximation and then get something like this. So in other words, sorry, Ri can be, this is divided by Q squared. This is Q overall squared. So you know what is Rp, you know what is Rin, right? And you also know the Q. You can figure out what is the value of Ri in a very approximate way. It need not be very accurate. Okay. Now, given a certain Ri, you can always go back and figure out what. So the first step would be to determine from Q overall Rp and Rin, determine Ri. Okay. Now once you determine Ri, what you can do, you can find the value of, find L, which is nothing but what? L1 plus L2, which is equal to Qri divided by omega naught. Correct. Now then what happens? You can basically go ahead and find out what is the value of C1. C1 is basically Q left divided by omega naught Rin, and C2 can be written as Q right divided by omega naught Rp. Okay. So with these things you can basically figure out the R, L and C, the C1, C2 and L values which are required to give the pi match network. Okay. Now similarly for an L match network, of course I didn't outline a design procedure. You know the value of Q. So suppose, okay, let me just say design of L match networks. Okay, let's take the same example. F naught is 1 gigahertz, and you have to, let's say Rp is 50 ohm and Rin is, let's say, 12.5 ohm. Now here what happens is, the first step is you need to find Q. Okay, find Q. It's easy to find Q because you know that both of them are related by a factor of Q squared plus 1, right? Now once you know Q, basically you need to subtract. Either you can take a low pass network or a high pass network. Okay, so let's say select high pass network or a low pass network depending on what you need for your this thing, and then use the Q equations, use the Q expressions for L and C. So let's say you have a network like this. Let's say this is Rp, let's say this is C and L. Okay, so Q is nothing but omega naught C Rp, and it is also equal to what? Omega naught L divided by R in, right? Because Rn is the series resistance with L, correct? So using these two Q expressions, you can find out the values of L and C. So definitely here you don't have any control over Q. Okay, all right. So this is how you design. So hopefully you pick up how to do the designs. I'll also try to give you some example problems. Okay. Now there is the dual of the pi match. So before I move out of pi match, you can the low pass pi match which I gave you was this, right? Right. The high pass pi match can be just a complement. Basically, you have two inductors and you have a capacitor, right? Now, typically for IC implementations, always have this in mind that inductor is extremely bulky. Bulky in the sense that inductor consumes a lot of area. Okay. Typically at, let's say, the lower gigahertz frequencies, that is like, let's say, up to 5 gigahertz and or up to 5-7 gigahertz, the inductor sizes typically the size of a typical inductor will be somewhere in the range of 250 sorry, that will be even more than that. Okay, so let's say around 250 micron cross 250 micron. This is a typical number, so it can go slightly above, slightly lower, but this is a typical number. Okay, now 250 micron by 250 micron is actually a very large area. Okay, when it comes to ICs. Okay, in this area of 250 by 250 micron, you can pack a lot of circuits. Okay, lots and lots of circuits. All right. In fact, I'll show you some chip micrographs where you would see that the inductors are the ones which are consuming all the area. Okay, because as you go higher in frequency, the dimensions come down. But then, typically in the mobile communication region, these inductors occupy quite a large area. Okay, so you try to avoid the use of inductors as much as possible. Okay, it's only in places where you really cannot avoid using an inductor that you end up using inductors. Otherwise, the typical tendency is to avoid using inductors and transformers. Of course, at very high frequencies, you can't do anything else, you have to use, but typically that is the first optimization criteria that you will have for any RFIC design is minimize the number of inductors. Okay, so which is why typically this is not used. Okay, now the dual of a pi match network is what is called as a T match network. Okay, now it's quite easy to understand. It will basically be something like this: C1, C2 and L, and as I mentioned, it is also possible to have L1, L2 and C. Okay, this is also a T-match network. Both can be used. As you can see, one has a high pass property and the other has a low pass property. Okay, so you can basically use whichever one you want. So here, because it's a dual, let's say it's a series resistance RP, RS, and you have a, let's say, RN. Okay, now what happens? How can you design this network? Okay, so the way to understand this network, let me use this for example. I mean, you can always use you can use the other one also, not an issue. So this can be understood as what? L1, let's say C1 in shunt with C2 and L2. Okay, so now here you get your intermediate impedance, right? Let's say you have your RP here, or it's not RP, it's RS here because it's in series with the inductor. Okay, and you get a certain R in. Okay, so the same set of equations can be used. I mean, the same way of writing things can be done, right? So the Q overall can be written as what? Let's say Q overall can be written as, it's Ri in shunt with C, so it is a omega naught Ri C, which includes C1 and C2. Okay, all right. Now Q right can be written as what? Q right can be written as the resistor in series with the inductor. Okay, so it becomes Ri divided by R S minus 1. Okay, which is also equal to, let's say, omega naught L2 divided by Rs, which is also equal to omega naught C2 into Ri. Same way you can define for Q left. Okay, Q left can be written as what? So here what happens? RC. So will Ri be greater than Rs or lesser than Rs?
Lesser than. Sorry, Ri will be greater than Rs.
Greater than Rs, right? Because this is an upward transformation network. So Ri will be greater than Rs. So basically what you're doing is you're taking the impedance higher and then converting down lower. Okay. Whereas in the case of a pi match network, what you're doing is, okay, if you look at this pi match network, right, Ri will be lower than Rp and Rin will be higher than Ri. So which means you take the 50 ohm, bring it really down, and then you take it up to whatever impedance you want. In this example, you want a 12.5 ohms, so probably you will take 50 ohm, bring it down to something like 5-7 ohms, and then bring it up to 12.5 ohms. Okay. Whereas in the T match network, it's the other way around. Okay, where you take the impedance higher, so you will probably take 50 ohm to something like 70-75 ohms, and then you bring it down all the way there from this thing to 12.5 or whatever you need. Okay, so this divided by Rin minus 1. Again, you can write the equation very similarly. You can the approach is very similar, same type of equations you write, and same design procedure is followed. Okay, all right. So there is one more thing. Let me just briefly give this. Tapped capacitor resonator also can be used as a impedance transformation network. Okay. Now this is sometimes used in oscillators. In fact, the pi match network has a very good advantage, which is that it has the C1 and C2 in shunt. Okay. So let's say you have a certain let me just go here and okay, as an aside. So let's say you have a transistor, and then you want the output of the transistor to be the impedance seen here to be lower than the other thing. You can easily put a pi match network. Okay, and the advantage of the pi match network is there will be parasitic capacitance at the drain of the transistor, right? So that can be absorbed into this C1. Okay, which is why pi match networks are quite preferred. Okay, now that as an aside, let's look at the tapped capacitor resonator. So as the name suggests, there is a, let's say there is a, let's say this is R2, and because it's a resonator, you have an inductor, right? And you basically have, let's say, Ra. Okay, so L, C1 and C2. So because you have two elements, you can always have 3 degrees of freedom. The exact derivation is quite laborious. I am taking this impedance transformation material from a book called as Design of RF CMOS Integrated, or I think it is Design of CMOS RF Integrated Circuits. Okay, I don't know whether, yeah, radio frequency integrated circuits by Thomas Lee. Okay, so this is another. This was one of the pioneering books in this field, and the full derivation is given there. But then, basically, roughly the ratio, happens to be something like this. The way to understand it is that there is a capacitance division, which yields a certain voltage division. So whenever you have voltage division, and if you assume it to be a lossless network, the impedance goes by a square of that. Okay, so R2 by Rn can be written as 1 by SC2 divided by 1 by SC1 plus 1 by SC2, the whole square. Okay, and this, if you kind of do a little jugglery, you basically get C1 by C1 plus C2, the whole square. So this is basically your transformation ratio. So the reason why we do a square is that when you have a voltage division, the impedance division ratio, in order to preserve for a lossless network, in order to preserve the equality of the input power and the output power. Okay, if you have no loss in the network, input power is equal to the output power, and in order to preserve that, what happens is when you have voltage division, the impedance ratio becomes square of that. Okay, So that is how you get it, and this is how you have it. You can also have tapped inductor mats and things like that, but usually those things are not used so much. Okay. Okay. And then another way, or another very commonly used, impedance transformation is basically to use a transformer. Okay. So you use a transformer. It is possible to build transformers on chip. Okay. They might have some 1:n ratio and so on. Turns ratio can be there, but the way the transformers are built are like this. Okay. So just to give a little, I think a little background on chip design and so on. If you remember, I told you that you have the substrate, right? And you have the interconnection metal layers, right? So you have metal layer 1, and then you can have metal layer 2 all the way up to, let's say it's an 8 metal process, metal 8 will be at the top. Okay. Typically what happens is the thickness of this metal lines are not uniform. Okay. So in the 65 nanometer process that you'll be using for your projects and assignments and so on, the M1 to M6 have the same thickness. Okay. And M7 is thicker than M6 or the rest of the metal, and M8 is the thickest. Okay. So I think the thickness of this is around 3.25 micrometer in this particular process. This thickness is around, I think if I remember right, it is around 0.4 micron. I think these are around 0.2 micron or something. Okay, or maybe this is 0.5, something like that. I don't exactly remember the numbers, but something like this. Okay. So what people do is, in order to form an inductor, okay, so how do you form a normal inductor? In your school you might have used some or even in some of the machines lab you'll use these auto transformers. So basically you have a coil being wound around a core, right? That is how you have these inductors. Of course, those inductors will have very high values like millihenry inductors or microhenry millihenry inductors and so on. Okay, and of course there are different ways of implementing. So you have air cores and you have some magnetic core and all those kinds of things, right? Now on a chip, how do you form an inductor? Okay, so you cannot have large inductors and so on. You are restricted to micrometer sizes only, right? So the way you form an inductor is basically like this. I am drawing the top view, okay, which is also basically your layout view, right? So for your layout view, what happens? So how you do it is, let's say you take, I'll just draw a spiral inductor, okay. Okay, so let me just, I know my diagram is very bad, but I hope it kind of conveys the point. Okay. Or see, this can be in circular or in octagonal form. So let me just draw a, this is two-turn inductor, okay, and then you kind of come out like this. Okay, coming out I will explain separately. So let's say you have this is the metal trace. Just for the sake of the class, just think that this is a circle. Okay, all right. So what happens is you put this metal layer in a circular form, okay, and then you come till here, and then you put a bunch of VRs, okay, and you take it to metal 7, and then you have an underpass. Okay, this is what is called as an underpass, and then you come here again, put contacts and come out in metal 8. Okay, So this is your top, the whole thing is done in the top metal layer. Okay. In this process, we have an 8 metal layer process. There are other processes which have little more, little less. Okay, whatever it is, usually inductors are done in the topmost metal layer. Okay, and the topmost metal layer you do, and just the underpass will be in the n-1 metal layer. Okay, so depending on the value of inductance that you need, okay, so there are some closed form equations which give you an approximate value. Usually these are, properly simulated by running some electromagnetic simulations. Okay, and that will give you the most accurate value of inductance and Q and other things. Okay, so this basically has a certain outer diameter. Okay, outer diameter, width of the line, and then you also have spacing, right? This is the spacing, okay, and number of turns. So all these factors basically determine the L and also the Q. Okay, of course, what is not in your control is basically thickness, conductivity of this metal and other things. Okay, now this is how inductors are done on chip, and usually the range of inductors is like, up to, let's say, maybe 12 nanohenry, something like that, not more than that. That itself is quite large. Okay, maximum probably around 10 to 15 is like really pushing it too much. Okay, so that's the range of inductors that you would get. Lesser than this is what is possible. Okay, you cannot think of microhenry, millihenry, and all that. Forget it. Typically, the range of inductors is like in the single digit nanohenry, or even slightly less than, a little lesser than 1 nanohenry. Okay. Now, it can either be a circular spiral, it can also be a hexagon, or it can be an octagon, or it can be a square. So all these different shapes have been tried, all these different shapes have been used, okay, and they are being used in practice. Okay, so this is how an inductor is done. Now, how to do a transformer? To do a transformer, what you would basically do is basically to put one more metal layer under it. You can have either a metal layer, let's say metal 8 and metal 7, or you can have two metal lines, running parallel with each other, such that there is some kind of coupling between, the first metal layer and the second metal layer. Okay, so, or rather the primary side and the secondary side. Okay, so the I think it will be better if I can show a picture. So transformers and balance are quite routinely used. Let me see if I have it open. Right. So, okay. Let's see. This is one inductor which my PhD student had designed. Okay. So this is at 30 gigahertz. You can see that this is a 1.5 turn inductor. Okay. So it comes in like this. This is the top metal layer, and it goes around like this. And this is the pass. You kind of go down to metal 7. This other color is metal 7, and you come out. Okay. So this is a single turn, 1.5 turn inductor. Okay. This shows the, this is the zoomed in version. All the small squares that you see here are all VRs. Okay. So he has put some, I think, 7 cross 7, 49 VRs, and then taken it down to metal 7 and then used it. Okay. Now a transformer is something like this. Okay. So this is one way of doing the transformer. Let's say this is the primary side. Okay. Now the way in which this transformer is done is the primary and secondary are running adjacent to each other. Okay. So just follow my cursor. So this is, let's say, the primary side. This is your secondary side. Okay. The primary is the outermost thing, right? And then here it crosses over to n-3. Okay. Whereas the secondary side is coming in at the second one. Okay. Here it is coming to the second one, and then it will cross over to the fourth one. Okay. So this is a 4:4, 4:4 transformer. Okay, and this 4:4 transformer is basically going to give you the impedance transformation from this is probably the primary side, the secondary side. So it will have a certain mutual inductance and a certain coupling factor, and based on that you are going to have a certain transformation ratio. So I'll just derive, or I'll show you the derivation of the impedance transformation ratio. But this is how a Balun is a transformer is implemented. Yeah, someone had a
Sir,
question.
by 4 into 4 you mean it's cover 4 layers?
Sorry, can you repeat the question?
Sir, by 4 into 4 you mean it covers 4 layers?
Not 4 layers, 4 turns. Okay, so it is like, the primary has like 4 turns, the secondary has 4 turns. So if you count it, you'll have 8 layers here, 8 metals here. So all this is on the same layer. See, this color is metal 8 and this color is metal 7. No other metal has been used.
Okay, sir.
Okay,
Sir,
so it
why
is
there are
plain as.
some open ends?
Yes. Sorry,
There are some open ends actually.
not open end. This is where it connects. Okay, this is the input
In
port.
between, sir.
Yes, sir. It's like second from the yes, sir. The second from the inner side.
From the inner
Second
side,
from.
second one. Yeah.
Okay, probably. Okay, where is this going?
It is connected, but some of them are actually just open. Like one coil, one round is actually open.
One round being open. Actually, one thing
There
could
are 4
be.
opponents, sir, in
Yeah,
total.
yeah.
Yeah, you have this. Yeah, these two, right?
Not 4, sir. 6.
Yes,
3.
sir. Six. Yes.
You 1, 2, 3, 4,
No, sir. Those are
5, and
connected to the outside. The left.
yeah, this is connected to the outside. You only have.
Yeah.
I think this is the end points.
Okay.
Yeah.
But
So
in the
I
previous
mean
case,
you.
you connected the endpoints, right?
Actually, one thing is you. I think you'll have to zoom in and see in the actual layout. This is a snapshot of the layout. It may be that they have connected it in metal 6, because you can see there is one square here, right? Like there is one sort of a cut kind of thing.
Yes, sir. Yes.
Yeah. So it's possible that it is going in the even bottom metal layer to just short these two. Okay, because this I think is the, I don't know if it's the secondary side or something. So
Sir,
yeah,
sir, are these metal or silicon?
metal. These are all copper metals basically. Okay, underneath.
Okay.
So you are looking at the top view. Okay, this is the top view. All right. Underneath is the silicon substrate.
Okay, sir.
So
And sir,
think of it like a multi-storied building. Okay. So the foundation is basically your silicon substrate, and then the ground floor is basically where you put your oxide and form the gate and so on. Then first floor, second floor, like that, you have many interconnects happening. And now what you are doing is you are kind of looking from the top. Let's say you are using your drone and taking a picture. This is the top view. All right. So
sir, why do we use only metal 8 and 7? Like, is there
yeah,
any
because
reason?
there is a very specific reason for that. As I mentioned here, right, the thickness is highest at the top metal layer. Okay.
Okay.
So the losses associated with the inductors become minimal when you use I mean, the thicker the metal, the lower the loss. Okay. So these inductors will basically have different types of loss. Okay. And maybe let me just give it now. If you look at an inductor, okay, the model of the inductor is something like this. You have an inductor, it will have a series resistance RS, because it is a metal layer, it will have some series resistance. Now it will also have a shunt resistance which is formed due to the eddy currents which flow in the substrate. See, the silicon substrate has a certain conductivity, okay, not conductive as metal or anything, but it's a slightly doped silicon, so it has a certain conductivity. Now because these things are going around, it sets up some eddy currents in the substrate, okay, and because of that, because of the loss in the substrate, you have some eddy current loss which is modeled like this, and you will also have a parasitic capacitance between the two terminals. Okay, let's say Cp, and you will have some capacitance to the substrate. Let's say this is capacitance. Let me just call it Cp. Let's say this is Cp1, Cp2, Cp3. Okay, and it reaches the substrate. Here the substrate has some resistance and some capacitance because it's not a full conductor, right? So let's say this is the silicon resistance and this is the substrate resistance, a capacitance C sub and the silicon resistance. Okay, so this is more or less like the model of your inductor. Okay, and the Q of this inductor, of course, this is a very complex model. Okay, at the end of the day, you can see that there are some bunch of capacitors, resistors, and inductors, right? So any inductor which is implemented not only on chip, any off chip inductor also, if you go to, let's say, Coilcraft and so on, they will specify that it has a certain Q factor, quality factor, it has a certain self-resonant frequency. Now, your actual inductor has some bunch of capacitance around it. So we define what is called as the self-resonant frequency, SRF. Okay. This is basically where the inductor by itself will start resonating. Okay. In other words, the way you see it is where the imaginary part of this whole, let's say this is a network, right? The imaginary part of this Z, crosses 0. Okay. And beyond SRF, this whole structure behaves as a capacitor. All right. So usually, let's say an inductor which is, let's say, designed to be used at 1 gigahertz, its SRF will be around 20 gigahertz or something. Okay. Usually, you try to keep the SRF as far away as possible from your operation region of operation. So if you are operating at 1 gigahertz, you want your SRF to be at least greater than 7 or 8 gigahertz or beyond 10 gigahertz, so that it doesn't affect. Okay. And you also define the quality factor. Okay. Now this series resistance RS, okay, also has two components. Okay, one is the ohmic component, which is basically it has a certain resistivity and you get some resistance. It also has a component which is frequency dependent, and that comes because of skin effect. Okay, I'm sure all of you have studied about skin effect. What is skin effect?
In a metal, the signal actually, high frequency signal goes through the surface.
Correct. So the current, if you see the high frequency current, the profile of the high frequency current across the cross section of any conductor, the higher the frequency, the more the current tends to flow in the outer, edge of the conductor. So if you say a circular conductor, the current density is highest here. Okay, the current density will be, if you plot current density in this axis, the current density will look something like this, right? Current density will be, and if you take the cross section, and even in this thing, it will be basically like this, right? So at the edges, you will have a larger current density and lower current density in the center of the conductor. So which is what is called a skin effect, and it is inversely proportional to frequency, right? So it's a frequency dependent thing. Both will come into the picture. So a quality factor, usually you will have around something like 7 to 12, 13. That's the quality factor that you can get on a CMOS chip. Okay. So these are the limitations that you have while realizing inductors or transformers on chip. And in transformers, you can always, as I mentioned, either you can have a certain transformation ratio, or I will just put up another PDF where I have derived the Balun equation. This is also called as a Balun. Okay, a transformer can be called as a Balun because it converts a single-ended to differential signal. Okay, so for example, this is the center tap. you have a, let's say this is a single-ended signal. Okay, this becomes a center differential signal. Okay, the center tap can be given to a bias voltage or to ground. So this is single-ended. This becomes differential. Okay, so in the old audio world, this was called as balanced, and this was called as unbalanced. Okay, so which is why this is called as a balance, balance unbalanced converter. It also is called as a balance, which is nothing but a transformer with a center tap. Okay, so usually balance are used. These can be used for impedance transformation also. Okay, so I don't have the time now to derive that. I'll just upload a PDF. It's very easy. You just talk about certain mutual inductance, and primary side inductance, secondary side inductance, and you can have impedance transformation. Many times, especially for power amplifiers and so on, you use a Balun for impedance transformation plus single-ended to differential conversion. Okay. All right. So with this, we'll conclude today's class. Are there any questions? Are there any doubts? Okay. All right. So thanks everyone. We'll meet again tomorrow.
Thank you, sir.